Good morning and welcome to what could be the most important session and topic of the whole course. So I'm glad that you took the time, made the effort to show up. As always, can I just get confirmation in the chat, ideally both YouTube and Discord, that you are hearing and seeing me as you should? Then we can get going. Perfect. Now let's get a new page going here and remember where we are. All right. Now, yesterday we reviewed our properties and realized that there is another way to combine functions by what we call the composition of two functions, let's say f of g of x, that we can't handle with our existing derivative properties. Now remember, our goal is the same here. We want to come up with ways that work to find the derivative of a function without using the limit definition. So we found that if we had a power of x, great, we can handle that. We have other properties to isolate that power of x. Great, they're important. Sort of support properties. We have ways to handle the addition of functions, subtraction, multiplication, division, but not this guy, not this guy. So let's just review how we need to look at this. We're going to have a function, so we're given some function. Call it f, call it whatever you want to call it. And let's keep it extremely simple. Let's suppose it's x squared plus 1. Actually, let's make it even simpler. Let's go 3x plus 1 squared. Let's go with that. Now our goal is to find the derivative. Now you might say, okay, well, in this case, I don't need to see this as a function of a function. I can FOIL it out, great, and then go about my business with my existing properties. Sure, totally could. But what if that power was higher? Do you still want to FOIL it out? I bet you don't. So I'm taking a small example because we have a way to handle it. Let's suppose the old way. Nothing wrong with it, but it relies on the fact that I don't have too many brackets that I need to multiply. So because it's a bracket squared, my old way is to simplify first, and I can definitely handle this. Simplify first to see the function as 9x squared plus 6x plus 1. We can all do that. Then we find the derivative with our existing properties. That is a sum property. We have a constant times a function property. Then we can do the power rule. We have a constant property at the end there. A whole bunch of properties, but we are more comfortable with them because we've seen them. We've gotten used to them. We've practiced them. They are feeling a little bit better. So we'll have 18x plus 6. And of course, I shouldn't even have to say it, but if you have any doubt about the 18x plus 6, then this is not the lecture for you. You need to go back and watch this as a recording later. You will just get confused. We need to build this up correctly. So certainly, totally fine. Nothing wrong with it. It'll work. But hopefully you can see that this old way isn't always going to work. If I don't have an option or it's too time consuming, too much work to simplify first, what do I do? The new way is to identify this as a function of a function. So let's say here, identify function of a function property or whatever. It's a composition of two functions. And that means I want to know what is my, it really doesn't matter. I think we wrote it the other way around. No, we started with the inside function. Inside function, that we'll call u, for no reason whatsoever. I could have chosen any symbol, which is the obvious 3x plus 1, because the brackets sort of give it away. There's not much choice there. Once I have made that decision, the outside function is kind of fixed to go with it in order to get my original function back. I have no choice. I have to have a u squared. Now I write it in this way to see the link between these two and how they sort of attach to each other, how they compose with each other to give me my original back. But they come in pairs. In some cases, not really in this one, in some cases, I have a little bit of flexibility to choose an inside function. But once I do that, the outside one is a specific function that goes with it in order to get my original back. I don't have much choice. So I chose the obvious inside function here, which is completely appropriate. So now, how do I use this? So this is where we sort of stopped. We can make the function more complicated, but we have so far just gotten to this point where I can break it up into an inside and outside function. Sometimes I have choices, sometimes I don't really have much choice. How do I now use this to find the derivative? This is where the chain rule comes in. The chain rule is going to tell me how to combine these functions to find the derivative of the original. Now we'll apply it, but I have to write it in general first, I think. So let's keep our names the same. Let's suppose we have an inside function. Inside function, so let's say given f of x. That's my given function. We have looked at it, just like in our example. We have found an inside function. Let's call it u. Now note here that u is a function of x, right? It's defined in terms of x's. So I want to maybe just keep that in mind, and I write the brackets with it to remind myself when I talk about u as a function, x is the independent variable. With it will go my outside function that, just like we did here, we'll call f. Well, it's the name of the original. And as far as that function is concerned, its variable is u. So u. So the key here is to look at these sort of with blinders on. When I look at the inside function, there is nothing else. I see that as a function in x, which it is. When later on I look at the outside function, I see nothing else. This is a function, as if there is nothing else on the page. This function happens to have a variable called u. Doesn't matter what the variable is called. It's just a function. Okay, that is going to help me a lot. Okay, let me take this box off. we go. Okay, so I have this set up. I have a function in u, which is going to be my inside function, function of x. I have a function called u, function of x. I have an outside function, which is going to be named the same as the original, and that's going to be a function of the variable u, which is always going to be the name of my inside function. Okay. Then, now here, remember we have different ways of, I'll do it at the bottom here. We have different ways of naming the derivative. We have, just in general, let's call the function g. We have the prime notation. We have the big D notation. And we also have the little d notation. They're all the same thing. In the case of the chain rule, the little d notation is going to help me remember this and set it up correctly. So I'm going to write my little d notation. My original function's name is f. My original variable is x. That's what I'm looking to find. This is the same as f prime of x. Exact same. I'm using the little d notation because when I look at this big picture, it's going to help me set this up. The chain rule says I'm going to have two parts. I'm going to have, let's do it with colors. Let's use some colors. I'm going to have a pink part, and I'm going to multiply that. Multiply. Come on, get away from me. I picked the color, now there we go. And I'm going to multiply that with a blue part. It's going to be two things multiplied together. The first thing is going to be the derivative of the function with respect to the inside function as a variable. The second part is going to be the derivative of the inside function with respect to the original independent variable. Now this looks much worse than it is, perhaps. Maybe it doesn't look bad, but it looks different to our other properties. Let's at least say that. So let's just see how this works with a specific example. And the more examples we do, the better it's going to get. Okay. So I'm looking for the derivative of my function is called f. The original variable is called x. The chain rule says take the derivative of the function with respect to the inside function variable times the derivative of the inside function. Now, when I do this, I need to look at them separately, meaning when I look at the first guy, I do not care about anything else that is happening here. That'll come later. I look, what do I need to find according to the instructions of this pink box? This pink box says, look for a function f that has a variable u. That is this guy. I literally see nothing else. There is nothing else that I am seeing right now. I look at that function, which has the appropriate function name, the appropriate variable for this derivative. That is all I care about for the immediate future. But of course, other things are written there, so I have to train myself to not look at it. That derivative is to u. Is everyone happy with the 2u? You came all this way. You can get the advantage of a live session by asking questions in real time that the others do not. Get that advantage. Set yourself apart. It's worth it. There's a benefit to sometimes watching a recording, scroll back and forth, pause, think about it, yes. But if you have questions, you kind of have to wait. Live, ask them now. We are not in a hurry. ask your questions to you. If you don't ask, I don't know where you're at. Next, I have to look at the second part of what I'm instructed to do by the chain rule. That says, take the derivative of u with respect to a variable x, which means I'm looking for a u function that has a variable x. So right there. And again, when I do the second part, I see nothing else. I don't care about anything else that I have done. It doesn't exist. And I emphasize that because I've seen many people get confused and overwhelmed because they want to do multiple things at the same time. They need to find the second part of the chain rule, but they're still thinking about the other part, and they look at a combination of things to do something. No, you have to train yourself, put blinders on, and only look at what this piece tells you to look at. You can save a lot of headaches, avoid a lot of headaches if you do that. But it takes training. Look at all these things written down, colors and all kinds of things distracting you. Yet I see none of it? Yes, none of it. You only see the two blue boxes. It takes time. So, I have found a function called u. It has a variable x. Its derivative is 3. All right. Now, I can simplify this to 6 times u. However, I'm not done technically. My original function was f and had a variable x. There were no u's in the original question. Technically, the u inside function was my choice to help me set up the chain rule and find the derivative. I didn't have to choose that. I could have done it the old way. And then my answer is in x. So the u being the choice that I make to find this derivative, I can't leave my answer in terms of u. That's not the original variable. I have to write it back to the original variable, but that's not a big deal because this u is over here and it is the same as 3x plus 1. So I simply substitute what u represents in terms of x, and then I'm done. So don't forget this last step. The u is my choice. Someone else could have called it something else, right? The u was a choice. So you don't want to leave your answer with that choice. You want it to be in the same variable as the original question was, as the original function was. Now, do these match? Yes, they do. Yes, they do. The derivative is unique. If I'm finding the derivative, there is only one answer. How I find it? Well, sometimes I have a choice. Now, this seems, for sure, like an unnecessary thing to do. I just simplified it and found the derivative. Why do I need this chain rule? Well, many times I won't be able to simplify, and that's just not an option. If you have the option, great. Think about which one you want to do, and I would definitely do the first one because it's faster. But most often, you don't have a choice, and simplification is just not going to get you around these fancier properties. It's just not going to happen. Okay, so whether you think about the chain rule in general, whether you simply take the time and with each example it's getting a little better, a little better, a little better, doesn't matter. I'm never going to ask you to state the chain rule in general. It's applied to a specific function. Let's leave this open maybe and go to another page. I might as well go to some problems. Why not? I think it's problem time. Unless you thought of a question that you might want to ask. So now, number 1 is very similar. So maybe I'll skip that one and go to number 2. I am not going to show these and flip back and forth because I make copy errors. I'm just going to put it on my other screen and copy it from there. Feel free to check that I'm doing the copying right, because that's certainly step 1. Make sure you copy the right question and you copy it correctly. That's important. Okay, so I'm going to do number 2. Whether you call it y, whether you call it f of x, I have y equals f of x equals. So to just emphasize that, swap the y and the f. Some people like y, some people like f. I could not care less. I'll stick to my f. But it's good to mix them up if you get stuck always thinking about one letter, and then when that letter changes, then you're totally lost. Nah, you need to mix it up a little bit. Okay, so here, I hope it's obvious to everyone. I in no way want to simplify this. It's never going to happen. It'll take me, I don't even know. Assuming I don't make a mistake, oh my goodness, it's going to take me a long time. Don't want to do it. There's a better way. It's the chain rule. I need to see this as a function of a function. So I say, let's actually get more creative with the colors. And let's say my pink is my inside function. The obvious choice, x squared plus 5x minus 1, right? There's no other choice, really. Once I've made that choice, I'm then stuck with my outside function to match it, which is obviously should have been in blue. F of u, and I just emphasize the u for my personal needs. For u to the 8. That's all I need. So the chain rule says f prime, which is what I'm looking for, my notation that helps me set up the chain rule, and I'll say why in a second, comes in 2 parts. First part says, whoops, first part, did I do the colors right? Oh, I swapped them. Man, let's go back. My outside function was pink. My inside function was blue. I don't want to confuse people now if they match answers and try to see similarities. I'm sorry. That was a boo-boo. Big boo-boo. Okay, we are in pink. We called the outside function pink, so it should be this one. For u to the 8. And then the blue is u. You can call it u as a function of x, which it is. There we go. Back on track. So now the outside function comes first in the setup of the chain rule. When I deconstruct the composition, the inside function, for me, comes first. So it's the derivative of my function with respect to this temporary inside function as a variable that I call u, times the derivative of the inside function, which is, of course, in terms of x. Let's continue with our colors. Derivative of the outside function. Now I'm saying casually derivative of the outside function. I think that is correct. And I'm always going to mean with respect to this u, this inside function, as if it's a single variable, which is how we defined it. just to see if everyone is sort of still awake. I know why you would be sleepy around 12 o'clock, but rain makes me sleepy. What is the derivative of the outside function? I have my pink color. I'm ready to write, but you tell me what to write. I give you only easy questions. Easy, easy. 32u to the 7. Okay, we've done enough of the detailed properties to just do that in one go. I sincerely hope. Now the blue part. Derivative of u with respect to x. Well, I have the blue. I'm looking at blue. It matches. I'm not looking at anything that's not blue. If it's not blue, I don't see it right now. Of course, I have a 2x plus 5, but you should remember your brackets, right? So what the chain rule is doing, really, it's taking a fairly complicated function in terms of the composition and how it's built, and it's allowing me to look at two separate derivative questions, a pink one and a blue one. Look at the properties involved in the pink one. They're all basic properties. Constant times a function, power rule, done. Look at the properties involved in the blue one. All basic properties. Sum difference property, constant times a function, power rule, constant property, done. Yet, I am able to handle more complicated functions. So the chain rule really gives me a way to systematically find the derivative of a more complicated function by doing my simple properties. It tells me how to piece them together. So now I'm not quite done. I don't care about simplifying this. I don't care about multiplying the pink into the bracket or any nonsense like that. It is nonsense because I don't have any need to simplify. What I do need to do, however, is write my answer in the original variable, and I can't have a u left as my final answer. So that's not a big deal. I simply swap back what u is. That's the blue one here. It's x squared plus 5x minus 1 to the 7, and I still have the other bracket, and I'm done. Done. If you feel you need to simplify that, that's on you. That is not on me. I have no need to simplify that. I will simplify if I have a need to. If this is a two-part question and I need to use my answer in a follow-up question, then maybe I want to clean up my answer as much as possible to make my life better moving on. Sure. That's not the case here. I don't care about simplification. Any questions on how we're using the chain rule to piece together the derivative? Once I have this, it's just a matter of practice. Over and over and over and over until it becomes super obvious and straightforward. Because it's always going to look like this. It's always going to be the same thing. First part of the chain rule, second part of the chain rule. That's it. There is nothing more. But of course, it relies on, there's some steps involved here, right? It relies on me splitting it up into an inside and outside function correctly, remembering how to piece the chain rule together, then doing it. Remember to swap back if you see a u. There's some things involved, of course. It's the last property. We save the best for last. There's an easy way to remember the chain rule that you might like or you might not like. Totally up to you. I used a little d notation because, let me make my x a little nicer here. There are actually some properties to this. Now, the little d notation here, I will emphasize, it is simply a name for the derivative. A little d for derivative, f is my function name, then there's at the bottom there's an x, because x is my independent variable, so all those things need to be in the name. Fine. It is not a fraction. In any way, it is simply a name. However, there is an argument and there is a way to prove that if I see this as a fraction, let me just backtrack my circles here. If I forget what this is and I pretend it's a fraction, it turns out that these little guys, they're called differentials, they actually follow the same rules as fractions. I don't want to separate them, this is a name, but they actually can be manipulated in the same way as a numerator and a denominator, which helps me remember how to set up the chain rule. Because now if I temporarily see these as fractions, then I see, oh, there's a du at the bottom, there's a du at the top, then I get a df left at the top and a dx at the bottom. So I can use their fraction properties and cancel common factors like I would for fractions. And if I get the original back, then the chain rule is set up correctly. Now, this actually is a little bit more useful in fancier chain rule applications, where I can have multiple inside functions inside other inside functions, and so on. And then setting up the chain rule could be a little bit more confusing. Maybe I have an inside function u, and then in that is an inside function, sorry, that wasn't right, is an inside function v. Then I can have a more elaborate chain rule and check it by thinking about it as a fraction and getting the originals back. Chain rule set up right. We're not going to do that. It is how it works. We are never going to need to do that. We'll just do it in two pieces, a first part of the chain rule and a second part of the chain rule. But it might help you to use this fraction trick to make sure that you set up the chain rule correctly. Let's get rid of all that stuff. Oh, that's as far as I can undo, so I don't want to see any of that and make anyone confused. So use the fraction trick. Don't use the fraction trick. I don't care. It is there. Maybe you like it. Maybe you don't. I don't know. It's up to you. Personal preference. Let's practice some more. Let us see what is up. All right, I'm going to stick to problem 6.1 for today. I don't know which one to do. I don't want to go too fast. We have 15 minutes left. Let's go number 4. Again, I'm just totally guessing. You might not be ready for ones we've done or we're going to do. Maybe you are. Maybe it's too slow. Maybe it's too fast. I really don't know. I have my function. My function is square root of 3x squared minus 1. Now here is an example where there's really no obvious way without some advanced concepts to simplify this guy and get around the chain rule. It's simply not going to happen. It's just not going to happen. You need to use the chain rule. So I will. Maybe, I don't know if you guys like the color. We're going to stick to the color, at least for a couple. Won't make the mistake of the wrong color at the wrong place this time. My inside function, I will call it u. It's obviously going to be a function of x. I don't really write that, though you can. It's the obvious choice, 3x squared minus 1. We'll come to functions that have different choices. Maybe what day is it? It's Friday, so maybe Monday. Yeah, we'll make this a little bit more complicated then. We have another session set aside for chain rule because it is so important. It takes time. So it's good that it's over a weekend. You can think about the basics and then see how you go into 6.2 and then see if you have any questions, and then we can figure it out and make everything clear on Monday as well. So once I have the choice for my inside function, outside function's done, right? There is no choice here. It's the square root of u. Okay, no problem. We spent all of yesterday making sure we can split these up. So, chain rule says I jump between notations for my derivative as I want to. It really doesn't matter to me. But for the chain rule, I am always going to use the little d notation because of that fraction trick. I can verify to myself very quickly whether or not I'm setting up the chain rule correctly. And the prime notation, no, there's no guarantee that I'm setting it up. I've seen the prime notation in more complicated situations, fair enough, be very confusing, and people can make mistakes when they don't even realize it, because the variable in question for the derivative isn't always obvious. So this little d notation makes it obvious. That's my function f. That's the variable x. I want to be pink, right? Derivative of the outside function. And you see its variable is u. Times derivative of the inside function. And you see its variable is x. So these are completely separate derivatives. Completely separate. And it honestly doesn't make any sense to me why you would want to do these at the same time. The chain rule works because it allows me to look at these separately. Because each one only requires basic properties. Now you might remember, where am I? I want to be pink. You might be someone that chooses to memorize the derivative of square root of the basic square root function. Oops, where's my 2? 1 over 2 root u. You might not. It doesn't matter. If you're not, I simply want to see this as a power of the variable, u in this case, and then use my power rule to write 1/2 u to the negative 1/2. Doesn't matter. They're different forms of the exact same thing. I'm not going to rewrite it. I'm not going to do anything. I just do it the way I want to do it. Then the derivative of the inside function, which is obviously, I hope, 6x. Not quite done. I see a u. My final answer cannot have a u. But I literally change nothing but replace u for what it is. Something else that I've seen, you can take from my experience. Others learn from others' mistakes and be better. Many people, they remember, okay, I can't have a u, so I need to replace it. Okay. While they're replacing it, they also want to simplify at the same time. And then they make mistakes. Don't do that. When I do my replacement of u back to x's, that is literally the only thing I do. I don't move anything. I don't simplify anything. I do nothing but swap out the u for what it is up here in the blue. That is where mistakes happen. People do multiple things in one line. It goes wrong. Don't do it. Do I care about simplifying this? No. I care about not wasting my time. There is no follow-up question. The question doesn't specifically say simplify. I will not simplify it. And you can't make me. Because it's another step, and I might make a mistake. If you simplify, and it's your choice, that's fine, but then I'm looking at if it's done correctly. So you better make sure you do it right. It's a skill I already have. I don't need to do it every chance I get. I think we have time for one more. Which one do I like? Which one do I like? You know, I kind of like number 6. I don't want to skip number 6. Yes, there's always more. We have another session after this one on Monday, so what's the rush? I have a function. It is 1 over 2x plus 3 squared. Yes. Okay, now get ready. I'm going to ask you stuff. Oops, no. This is your moment. What is your first attempt, your first guess? What do you want the inside function to be? Don't think about it, just do it. Actually, I should never say that. I just want to know your first guess. Then when you think about it, you might realize there are other options. I don't want to, just want the first guess. And you'll find 90% of the time your first guess is going to be the most effective one, most efficient one. I have options here, yeah, and we'll look at them for sure as soon as you tell me what the inside function should be. Obviously the brackets, right? It's a perfectly good one to go with. Nothing wrong with it. Now you might not know, ooh, there are other choices. Am I going with the right one? If it works, then it's good. Just because there are other choices that could also work doesn't mean yours is bad. This is a perfectly good one. But of course, once I choose it, my outside function is kind of stuck to 1 over u squared. That's okay. No problem. Because we said last time, any choice is good if it gives me an outside function that I can find the derivative easily. It's straightforward, it's basic properties. And this one certainly is. Certainly. Okay, so then there's no need to overthink the inside function choice. So by the chain rule, I am looking for the derivative of my original function in terms of the original variable. Chain rule says, take the derivative of the outside function times the derivative of the inside function with respect to its variable. All right, let's do it. What property or properties am I going to use for the derivative of the outside function, the pink one? What is the main property that I'm going to use? I want to check. I want to know how you think. There could be multiple ones, but what is the first property that you're going to use? Because you have to know these things, right? You have to do it eventually. It is certainly the power rule. Now, you could look at this and say, but I have a fraction. It's the quotient rule. The quotient rule is not wrong, but it's overkill because I have no variable at the top. It's completely unnecessary. It's like you have a sledgehammer to knock a teeny tiny nail. It'll work. That nail's going in, but it wasn't necessary. Always aim for the simplest rule that you can to avoid mistakes. So seeing it as just the power of u, which I totally can, it's negative 2u to the negative 3. No problem. There are people, I can't say I understand them, but there are people that use the quotient rule for this. It won't be wrong, but why? Why would you do that? I don't know. I can't think of any good reason. But it would work. Always go for the path of least resistance. Simplest. Derivative of u, just 2. I'm very close to being done, but not quite. Because I see a u, I need to replace it with its equivalent x representation. So I now make a point. I change nothing. Literally nothing but the u. I don't put the 2 in front. I don't do anything because that's where mistakes come. Should I put the 2 in front and make it a -4? Should I put the bracket underneath in the denominator and make it cubed? That's up to you. I don't care. I'm done. I've moved on with my life. Totally up to you. So feel free to simplify. If you have strong feelings towards simplification, I don't want to stand between you and your love for simplification. But when you do it, it better be right. So it's totally up to you. Well, that was the chain rule. Now, we're not done. We need more practice for sure. And you can see there are many more questions. But the essence of the chain rule is done. We just want to make sure that any kind of function, if it's a little bit more complicated looking at the start, how do I handle that? But the chain rule is not going to change. It is what it is. There are fancier versions of the chain rule, but they're not really different, and we don't need any variation other than the basic chain rule. So we'll continue with more examples on Monday, but I encourage you to have a look at the problems, see where you're at. If you have any questions, that's the time. That's why we have these sessions. Are there any last words for this week?
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.